Here's an example. We're going to find the mass of the planar lamina with density at point xy proportional to the distance from the y-axis. Now when we say proportional to the distance from the y-axis, that means the further away we get from the y-axis, the more dense it becomes, and we could say that our rho, our density function xy, is just some constant times x, because x is a measure of the distance from the y-axis. And we're also given this region. This is also part of the example. The region is y equals x squared, y equals 0, and x equals 4. So x equals 4 is this line, y equals x squared is this parabola. This would be the point x is 4, y is 16, and y equals 0 is the x-axis. So we're looking at the function, the density function, k times x over this region. An old picture I made of it kind of was like this, that tries to, I'm trying my best to describe what it is, but it's not perfect. And I hope you see that the problem with this is the scales are off. So the scale here, there's 4 this way, but in the in the y direction it goes up to 15, you know. So of course the z direction, I can't rotate this because I drew on it once I draw on it. So this is what it would really look like. I drew like f of x equals 2 times x. Maybe I'll just make it 1 times x. And now you can see, you can't see the parabola. The parabola would be, I'm pretty much outlining the parabola here. And so what we're really finding is the volume above this piece of the parabola, and yet still underneath the line y equals k times, actually the plane y equals k times x. And so there's just 1 times x, just to show you what it would look like if it was x over 2. There we go, that would be a half times x, see the difference? Or it could be like 2 times x, I think that's what I originally had there, 2 times x. So that's, oh, I didn't draw that one though, did it? Yes, it did. There it is. 2 times x. So keeping in mind, imagine that there is a parabola there. So that's what we're actually finding. We're actually finding the volume underneath this density function, whatever that density function is, and over this plane region. Okay. So how do we start? Well, if you make a stripe across this area, the top would be y equals x squared, the bottom would be y equals 0, and we'd start making those stripes from x equals 0 all the way out to x equals 4. So that should dictate to us our limits of integration. See, y goes from 0 to x squared, and x goes from 0 to 4 of k times x dy dx. That's not the only way. Another way we could do this same problem would be to set it up with our stripes of integrating stripes, if you want to think of it. The top would be x equals 4, the bottom would be x equals the square root of y, this way, and we'd start making the stripes here when x equals, when y equals 0, and we'd stop making those stripes up here when y equals 16. So this will give us the same result, x equals square root of y to x equals 4, y equals 0 to y equals 16. This one and this one should be identical. But I think I would probably choose to do this one because, you know, that's pretty nice, easy integration. Although it wouldn't matter, you'd get the same result either way. Integrating this with respect to y, we just get kxy. K and x would be constants, of course. And so we get k times x times y going from 0 to x squared dx, right? And if y is going from 0 to x squared and you put in 0, you get 0, so put in x squared for y here, we get integral from 0 to 4 of k times x cubed, which is k times x to the 4th over 4. X going from 0 to 4, that gives us 4 cubed, which is 64 times k, whatever the k is. Just so you know, if we did it this other way, integrating with respect to x first, we would get x squared over 2 times k. And that would be evaluated, oh, not if, sorry. that would be evaluated. Let me try again. That would be evaluated between square root of y and 4. So square root of y here and 4 here. Now when I put in square root of y squared is just y. When I put in 4, I get 16, but that's divided by 2. So that would give me 8. So it's 8 minus y over 2. And then we want to integrate this animal with respect to y. So this is going to give us k times 8y. Actually, I need parentheses around that. 8y minus y squared over 4. Then I can end my parentheses, and then I want to say evaluate that between 0 and 16. So I hope this comes out to be 64k, and if I put in 16 there, you can see I'm going to get 8 times 16. Oh, when I put in 0, I'm going to get 0, so that's kind of nice. So 8 times 16 is 128. 16 squared is 256, but that's divided by 4. 256 divided by 4 is 64, so I get 128 minus 64, which is 64, so I do get 64k, just like I thought I would, just like I did when I did it the other way. So that was a nice, interesting example, also showing you that you can change the order of integration. As you noticed before, sometimes when you change the order of integration, you can't integrate the darn thing one way, but you can the other, and that's always a nice, handy thing to know about.